Okay, yeah. Right here. Okay, well, thank you very much for the organizers, Colin, Joel, and Avishai for giving me the opportunity to present my work. So the work that I'm going to present today is just a preliminary result of a series of a study that we would like to do on how we can project the stellar to Halo mass relations into the inner distributions of these dominated galaxies. Let me put it in this way. Are the stellar to Halo mass relations that we are inferring from abundance matching or from HOD models are consistent with the Tully-Fisher relation, for example? So this is going to be my talk. So first, I will start with the stellar to Halo mass relation. So I guess that everybody is very familiar with this relation. So here we are showing the stellar to Halo mass ratio. We know that this stellar to Halo mass ratio, when we plot it as a function of Halo mass, has a peak around 10 to the 12, where we see that around 13 to 30% of the baryons were already formed. So what I wanted to highlight with this figure is that despite all these models that we've been using in order to infer this relation, most of these models converge to the same relation. I know that we have a lot of uncertainties and systematics in inferring stellar mass, but I think it's a great progress that we have been doing in derive similar relations despite of the different models that we have used. We also have a rough idea of how is the stellar to Halo mass ratio at different redshifts. But we know that above redshift 4 or redshift even 3, some people will disagree with this picture in which some of us don't see too much evolution along masses. We see some evolution around the peak mass. Others see some evolution at lower masses. I'm not going to talk about, but if you would like to hear my opinion about this, you can approach to me later, okay? Oh, and what I wanted to show you here is that even the models that have shown some evolution in this stellar to Halo mass relation, so the dotted line that we have here is if all the baryons were transformed into stars, is the universal baryon fraction. So even at different redshifts, we don't see that this ratio is close to the universal baryon fraction, okay? So what we can do with this stellar to Halo mass relation? So we can, for example, put this stellar to Halo mass relation in body simulations and show that it roughly reproduces the two-point correlation function. What I'm showing here, this is the two-point correlation function, different stellar mass beams. The dots are from the Sloan. The red solid line is the stellar to Halo mass relation that I showed before, or one of the stellar to Halo mass relations that have been published in the literature. You can see another examples that show the same thing here. And also, what I think it's an important result, and also Joel talked about this. So what if all the properties of the galaxies are just fixed by the Halo mass? So what we did in this work with the student Dragomir, so he did abundance matching in different bands from the U band to the C band from the Sloan. He did abundance matching. He also did abundance matching with the stellar mass and compute the stellar mass functions directly in the Bolshoi simulation as a function of the environment and compared to observations. And what he found was this remarkable consistency. And also, if you would like to see what are the predictions for conditional stellar mass functions, you can see that when you compare with Galaxy group catalogs like the Jan et al. Catalog, where you can compute the conditional stellar mass functions for different Halo mass beams, you see that the predictions that come from abundance matching, for example, which are related to the stellar Halo mass relation that I show, are very consistent with what we see in these Galaxy group catalogs. And also in one of the other papers, we showed that you can, for example, assuming a very simple model in which the stellar to Halo mass relation is independent of redshift, and just using the merger trees from the Bolshoi catalog, you can show that the specific star formation rates inferred from that model are very consistent with the observations. But then, what if we try to extend this correlation? So what I'm plotting here is, again, at redshift 0 or redshift 0.1. This is a work that Ruben is doing. So if we plot the baryons that you will see in the galaxies only in the galaxies, and you plot now the ratio of the baryon to halo mass to halo mass ratio as a function of halo mass. Of course, low mass galaxies or low mass halos will host will be gas rich dominated, and this will increase what we see here with the red line, the result of the baryon fraction. But note that it is too far from the universal baryon fraction. You just increase a bit around 50%. And we also know that the stellar to halo mass relations are different for blue-red galaxies. So here I'm showing some work that we did. The halo mass as a function of the stellar mass. We see that the main result is at a fixed stellar mass, red galaxies are hosted in bigger halos than blue galaxies. And when you put this as a fraction, now as a function of the stellar mass, this is the universal baryon fraction, you see that that halos hosting blue galaxies, they are closer to the universal fraction, but still they are not in the universal fraction. So what I'm saying this, because what I'm going to show now is that, well, we have another way to show the galaxy-halo connection. So here I'm showing the Tully-Fisher relation. So this is the Bmax versus the stellar mass. We know that it has a slope between 0.25 to 0.33 with a scatter around 0.05, 0.1x. It depends on what you are using in the stellar masses and how you predict and how you compute the Bmax. You will have this kind of uncertainties. But also we have the same for dark matter halos. So we are plotting here the Bmax from the halo directly as a function of halo mass. The slope is very similar to what we see in the Tully-Fisher relation, and the scatter is also similar. So, so if we want to project this panel into this figure, we will also have to do it through the galaxy-halo connection. So some people have been trying to do that. I mean, this is not new. Several people have been trying to infer halo masses from the velocity rotation curves or the Bmax. And this latest paper, I just put it. So I don't know if they are wrong or they are right, but they inferred the halo masses using the spatial resolved rotational curves. And what they found is this stellar to halo mass ratio compared to Moster et al. So what they found is that when they compare to the cosmological baryon fraction, there are galaxies that are very close to the cosmological baryon fractions, while the stellar to halo mass relations that I showed, they are not even close to that, okay? I don't know if this is wrong or right, okay? And I don't want to discuss that actually, because we can spend a lot of time to do that. But the problem here is that this is consistent with the Tully-Fisher relation. So my question is, are the stellar to halo mass relations that we are inferring from these models consistent with the Tully-Fisher relation? So when I saw this, the first thing that I just figured out is that probably this is just reflecting that the stellar to halo mass relation of blue central galaxies are bigger than, the ratio is bigger than red galaxies. So here the black solid line is like the analogous to the Moster, and this is the difference with the, for blue galaxies. So what I'm going to do is to produce a very simple model for this dominated galaxy. Our idea is what I said. We would like to project this stellar to halo mass relation, create somehow a galaxy here within our dark matter halo, create rotational curves, and then project into the matter to the stellar and into the distribution of matter as a function of radius of the galaxies. So our model is very simple, has these components. Of course, has a dark matter halo, has an exponential thin rotational supported gas disk, has an exponential thick isothermal sheet as a rotational supported stellar disk, has an exponential thick isothermal sheet as a rotational supported pseudo-bulge, and a classical bulge. So what we are going to do is we are not creating a population of individual galaxies. We would like to see average. So what I wanted you to imagine is that we will create a continuous series of models that you should imagine that we are stacking like the the profiles of the galaxies as a function of the stellar mass. So in that sense, if we are stacking the profiles of the galaxies, we can have galaxies, our average galaxies could have a classical bulge and also a pseudo bulge, okay? So what are the ingredients of the model? Well, we took the dark matter halos, the concentration to halo mass relation from the Bolshoi-Planck simulation. We take the stellar to Holo mass relation from our paper, 2015, that incidentally, they are consistent with galaxy clustering and galaxy groups. They were constrained, you see that. And they are consistent also with the results from weak lensing, okay? And we are also using the new relations that Ruben here, talk to him about if you want to know more details about these relations. What I'm showing here is the ratio of the gas to stellar mass as a function of the stellar mass for H1, H2, and the total gas, okay? The interesting thing about this is that Ruben did a very big compilation for, in the literature about these quantities. He divided into late types and early type galaxies. But in the distributions that he's constraining as a function of the stellar mass, he's taking into account all the upper limits. So in our distributions, normally people don't take into account the upper limits for, due to non-detections in the samples. So he developed a method, a survival method, to take into account that. So talk to him if you want to know more about this. And we already submitted this paper. We also showing that these gas distributions reproduce the mass functions. So what we are showing here is the bivariate distribution of H1 stellar mass, H2 stellar mass, and we reproduce the mass functions of H1 compared to alpha alpha, and also of H2. If you want to know more about this, you can approach me as well. And also, Ruben is extending the Galaxy to Holo connection. Perhaps you see his poster. But what I wanted to highlight here is that the correlations that we will use of H1 as a function of Holo mass are consistent with galaxy clustering of H1, okay? So coming back to our model, these are some part of the ingredients that we are using in the model. There are other details that I don't want to enter too much into that. You can ask during the question session, or during the breaks, you can ask me more about this. But the idea is to use as more empirical data or observed data and do as more as empirical model as we can do in order to avoid a lot of physical assumptions in our model, to be clean what is the things that are affecting most in our model, okay? So just keep in mind that we are using average models, okay? And that our galaxy could have a pseudo-bulge, a classical bulge, this galaxy that is thick, actually, and a thin gas disk, okay? So in order to create the circular velocity of our model, we need to add all the components of our galaxy. Here is showing, which is the thing that I show you here. But let us go to the results. So these are the circular velocity profiles. So I'm going for galaxies for 10 to the 9 to 10 to the 12. So you can see here all the components of our galaxy. As I said, we have a classical bulge, a pseudo-bulge, a stellar disk, gas disks, and the dark matter halo. And here, the arrows, you can see the classical definitions for the different types of Tully fissure. 2.2 effective radii, scale length radius, B80, which is the 80% of the stellar mass, and Bmax, okay? Here are our results. So what we are plotting here are the different definitions for the Tully fissure relation. So here is Bmax as a function of a stellar mass, B80 as a function of a stellar mass, at the effective radii, and 2.2 scale length radius of the disk, okay? The data is shown with the circles and the X. In every panel, we show which data we are using to show this. And the solid line represents our model. So the upper panels show as a function of the stellar mass, and the lower panels show this as a function of buried mass, okay? The different lines show whether we consider adiabatic contraction, and the green line is when we are when we didn't take into account the adiabatic contraction. So here we show that if we take into account the adiabatic contraction, we can get very nice results for the different types of Tully fissure relations, even for the baryonic Tully fissure relation. So we see that for lower masses, perhaps below 3 times 10 to the 9th, we see some curvature in our Tully fissure relation that is not present in the model. So perhaps this model should take into account adiabatic contraction, okay? So here we are presenting the different Tully-Fisher relations that we have in our model. Again, this is B, the different types of Tully-Fisher relations as a function of stellar mass and baryon mass. And here are the ratio between all of them against the Bmax. And in the lower panel, we are showing what are the main source of contributions to the scatter in the Tully-Fisher relation. So the surprising thing, when we believe that the concentration of the halo was like the major source of uncertainty, and you can see that it is actually one of the biggest sources of uncertainty, the gas mass was one of the biggest for intermediate to low mass galaxies, and the same in the baryon mass. So then, when we are projecting this into what is the ratio between the total, between the mass to dynamical ratio as a function of the effective radii for the different components, we have here that for most of the galaxies below 1 effective radii, so the dotted line shows the 50%. So pay attention to the gray line, all the gray lines, which reflect the dark matter halo, and the dotted line, which represent the baryons. So here is when they contribute to the same thing. It's the 50% of contribution. So for most of the radii in our galaxies, 1 to effective radii, we see that the contribution is around 50%. So perhaps in surveys like MANGA, you can already measure what is the contribution of the dark matter. They go around between 1.5 to 2.5 effective radii. So perhaps these are very interesting targets to study what is the ratio of the total to dark matter. Here's the same thing, showing the different colors are showing the different stellar masses, the total stellar masses of the galaxies. This is the ratio as a function of this for only stars, baryons, and dark matter. Okay, so you can here see that the 50% of the fraction lies around within basically 1 effective radii, I will say. Okay, this is another way to, this is another comparison that we did with some observations. So we are plotting the stellar mass and the dynamical mass within 1 effective radii. We are comparing to Aquino Ortiz, who will talk later today in the next session, and to Holo 2017. So just pay attention to the solid, sorry, he should be black line, to the solid black line to our model, which is our fiducian model, is basically reproducing what we see in the observations. And here's, again, another comparison, is the fraction of dark matter at effective radius as a function of the stellar mass. Here we are comparing, again, with the same data from Aquino Ortiz 2019, and we also as a function of the circular radius. Here we are comparing the 2.2 radii of the scale line. So the model seems to reproduce the trends and with the observations. And yeah, so in my last 2 slides, I will discuss a bit why I believe that why you should take care when you try to infer the halo masses from rotational curves, why you should take care about how the things you are doing. So we did the following experiment. So from our synthetic models, we have the stellar mass density profiles. This is the stellar mass density and the radius, okay? For different galaxies, a galaxy of 10 to the 9, 10 to the 9.5, 10 to the 10, and so on until 10 to the 11.5. So what we did is to refit to our models just to bulge and disk using 2 components, bulges and disks, and fitted our stellar mass profiles. Even though when our mass profiles were a bit more complex, because we include a pseudo-bulge and a classical bulge, we just decompose into 2 profiles, okay? And then we use this as a constraint and the rotational curves as a constraint, okay? We put a lot of points here just to get good fits between in our fit, and just decomposing again between disk and bulge. So we did, we tried to constrain the parameters of the dark matter halo, in the model, and we get this. Well, of course, the total stellar mass was recovered, but here's the surprising thing. Even if we just break this degeneracy between the disk and the dark matter halo, because we have the stellar mass profiles of the galaxies, as you go to larger mass dark matter halos, even if you can break this, just by the simplicity of dividing or using two components, disk and bulges, we get lower halo masses in the fit to what is the real halo mass of that galaxy. And we also obtained that there were very concentrated dark matter halos to what was the input of the model. So perhaps this doing very simple things in just decomposing rotational curves by just fitting your light profiles to bulge to disk probably will bias your halo masses when fitting the rotational curves. And here I led my conclusions. And thank you.
Okay, questions? Yes.
So I will be the first to admit that, you know, fitting rotation curves is a tricky business. But I don't understand in your case what's going wrong, because you made an analytical model and then you use the same sort of analytical model to try and fit your analytical model. So what is it, because you didn't include the adiabatic contraction, or what is the main source of the error?
No, we include everything, but we just assumed that there was a disk and a bulge. So what you see here, so here the X.
But that's what you put in the model also, right?
No, we are putting also a pseudo bulge. And here we are, and our disk galaxy is also thick. And here we are assuming a thin disk.
You started out the talk by showing us a fraction of the baryonic mass that you expect, the cosmic baryon fraction, that is turned into stars in different kinds of galaxies, and suggested that it might be a lot higher in disk galaxies than in early type galaxies.
Yes.
I was hoping that at the end of the talk you were going to return to that and tell us whether you think that was right.
Oh, I think abundance matching, well, I think our stellar to halo mass ratios are correct. So you mean?
Your very first, yeah. Well, actually,
you mean this?
Yes.
I think this is correct. I think this is not that bad. Let me put it in that way. It is not that bad because we are reproducing the Tully-Fisher relation. So there is not inconsistency as we see here. So this is the Tully-Fisher relation, but it's not reproducing the stellar to halo mass ratios.
Okay, any other questions? Okay, let's thank Aldo and the other speakers one more time.